Welcome to the C4G outreach of 2021. My topic was particularly about the state plane coordinates and the background for the legislation that will be required to recognize the new state plane coordinates. Why plane coordinates? We're going to start with a little background. Is the world flat or round? So in order to answer that question, let's review it just a little bit, get the concepts. Probably most of us will recognize that instrument on the left, a microscope, but it's a good metaphor for the concepts that we're dealing with ever more precise geodetic positioning. Take, for example, a piece of cloth. Looks nice and smooth with the eye. So a general overview can be modeled very quickly. But if we stick it under a microscope, the more detail we get, the more work it takes to describe what's really going on. Throughout history, as far back as ancient Greeks, they were 8 wind gods. They came horizontally. Each deity had a cardinal direction. The winds were associated with the seasons that they represented. I hope I pronounced them right, but Boreas is the north wind that brings cold air. Notus is the south wind that brings the storms. Zephyrus, west wind from the spring. And Eurus is warning of the coming winter. And there are minor ones for the northeast and southeast, northwest, and southwest. These were important enough to know which direction we were going in, north, south, east, or west. They were personified by symbols. These symbols I'm showing you here are on the londinoupolis images, which is an observatory, if you wish, that allowed one to find his direction, northeast, southwest, etc. They knew that the Earth was spherical, but placing things on it is a problem on the sphere. Latitude was pretty straightforward, usually using the pole star, but longitude was always a rough guess without and until we had accurate timekeeping. Now the moons of Jupiter and the ephemeris made it possible to begin getting accurate longitudes, but that didn't work so well for seafarers. Eventually, John Harrison invented a chronometer that began to make it possible to know where you were east-west or with longitude, even while on the sea. However, local surveying is typically still today a matter of plane, distance, and bearing from some starting point. Officially in previous times, it would have been from the town center. Many of the ancient towns had an obelisk in the center of the center of the community, and from which one could describe the property that they had or that they were selling or whatnot. Navigation, however, really was by spherical latitude and longitude, usually by stars and clocks. That's how it's been for a long time, with incremental improvements. But in the 20th century, in the United States, a continental-wide national datum became a reality. The horizontal datum of North American datum of 27 could be treated as a plane coordinates for surveys of very small extent, much like picturing an ant crawling across a beach ball. It seems flat to where he is. And this particular datum fit the area of interest, in this case, the local ellipsoid that fit North America. It wasn't related directly to the center of mass of the Earth. That was pretty difficult to... Excuse me a second, that's not supposed to happen. Amazing leveling campaign, though, resulted in the mean sea level vertical datum of 1929, later correctly renamed to the National Geodetic vertical datum of 29. And in the NAD 27, the Coast and Geodetic Survey developed a system of state plane coordinates for each of the states. It had a design distortion target of better than 1 part in 10,000, which was at the time adequate, and for most cases still is adequate for most boundary surveying. And it served us well for quite some time. But then the middle of the century happened, and in 1957, the Russians launched an artificial satellite called Sputnik. It started something new that created many possibilities for positioning, navigation, and surveying. Satellites necessarily orbit the center mass of the Earth, enabling global ellipsoid definitions that now are based on the whole Earth instead of being forced to fit the local areas, even if they're continental in scope. A little bit later in the century, the invention of the electronic distance meter and its common use had an untenable effect of giving surveyors the ability to make observations even more precise than the datum to which they were referencing. NGS responded to that by developing the North American Datum of '83, about the same time that the Department of Defense came up with WGS 84. Now, when created, they both were based on the Earth's center of mass within the known precision of the time, which probably was about 5 meters or so. However, WGS 84 was firmly defined to stay based on the center of mass, and 883 was pinned to reference points on the surface of the continent. Now, as I said before, the satellites help define by their orbits where the center of mass was, and our knowledge and the precision of the knowledge of where the center of mass has become positioned with amazing accuracy today. But that left NAD 83 a little over 2 meters away from where we've discovered the true place to be. It's a little like this now. This graph shows you graphically an offset from two identically shaped geoids, but with the origin in 2 different places. So in 883 and ITRF, in this case 0, which is effectively the same as WGS 84, is actually about 2 meters, 2.2 meters away. It's still within that 5-meter area that they began with. It's just that the NAD 83 wasn't allowed to move while the ITRF was following the best available data, with the result that there can be 2 sets of coordinates for any point you want to position based on the reference system you're using. Now, well, let me go on. Another thing that is important, and especially to us in Louisiana, is getting heights. The GPS system, and followed by other global navigation systems, has allowed for very precise ellipsoid positioning. In other words, whether it's 83 or ITRF, you can determine relative to that datum, that geoid, I'm sorry, wrong word, to that ellipsoid, you can get from your GPS equipment and system very precise ellipsoid heights as you can the horizontal position. The problem is that is not what determines which way down is. If you define down as the direction that gravity is pulling you here, then the unequal distribution of mass, you have water in the form of oceans on one side, you've got denser materials that are upland, and perhaps other irregularities such as a less dense salt dome, or maybe as you get in the mountains, you've got dense rock or metal deposits, a lead deposit. All of these affect you locally, that so that down is not pointing toward the center of the earth at your place. And the shape of the potential, or think of it as the shape of the strength of gravity where you are, or where everybody is consider that a surface. It's not unlike taking a topographic survey of a lot somewhere, a farmland. You've got the undulations you're showing. You can't see the geoid with your eyes, but if with great measurements, you can determine what those strengths are. And when you do, you can plot that out in such a way that you get what we might call a DTM, digital terrain model of the strength of gravity. It's a little simplified, but it fits the concept. So if you can figure out then how far is the space between that geoid and the more easily measured ellipsoid, you can combine the two so that you can use your GPS to give you an elevation, because elevations are based on the strength of gravity, not on your man-made ellipsoid model. This illustration has an extra component thrown in it called the hybrid geoid. We may be very comfortable with a certain vertical datum in North American vertical datum of 88 is its origin is pinned at a certain benchmark up in Canada and was the best fit for the time that it was created, but it doesn't match precisely the gravimetric characteristics of the Earth. And so in order to get the correct NAVD 88 elevations using a geoid, you have to modify your model from the real, what we'll call the real geoid, the gravimetric geoid, and add that little factor, the red lines you see in there, to create a hybrid geoid. And that's what we've been using. If you've been using your GPS system and getting an elevation out, somewhere in the software that you use in the receiver or in your computers later after you download your data is doing that for you. It's taking the ellipsoid height, which the GPS gets, and adding the geoid model to it. I'm going to go on from here. We'll be coming back to that in a little while. But anyway, by the late 2010s, NGS embarked on a new datum for the 21st century. It takes advantage of advances that we've made in both geometric and physical geodesy, and of course, in the advances of computing technology. I'm going to take it by steps for the concept of what's going into our state plane coordinate system and why we even need to bother doing this again. Step one is to come up with Earth-centered, Earth-fixed reference frame. It's basically a Cartesian coordinate system based with the origin at the center mass of the Earth. And the x-coordinate coming out of an arbitrary point, it happens to, for convenience, comes out through the point south of Greenwich, England, where most of the geodetic systems in the world today consider latitude 0. And the y comes out 90 degrees from that, also toward the equator. And the z is perpendicular to both of those and comes in and out of the mean polar position of the rotational axis of the Earth. Step two is something new for this project. They have taken great steps to determine the Euler poles of the different tectonic plates. And you'll see when we get to that slide why that is a great advantage for us, especially for those who want to use coordinate systems. And next, the gravimetric geoid has been improved and is being improved drastically right now in by having had some recent years, some satellites that directly measure the gravity potential as they orbit the Earth, and being high up and using the microscope metaphor, it's like looking with your naked eye and you get what they're calling the long wavelength geoid data. They're taking it a next step further using aircraft which fly to much closer to the Earth and getting what might be called the medium wavelength data, using, again with the metaphor, it would be a magnifying glass. And for truth control of the, or proofing of the data, you can do gravimetric data on the surface of the Earth, which would obviously be way too tedious to go further, or to have a great extent, but it helps provide the, and does a QC on the rest of the data. And step 4, this 2021 or 2022 version of the state plane coordinate system is being calculated in such a way as that it's scaled to best fit the topography of the area that the coordinate zone fits or is intended to apply. There will be 4 terrestrial reference frames for your information. The one that most of those in our audience are going to be interested in is NatRev, or the North American Terrestrial Reference Frame 22. Heights will be based on a geopotential datum instead of the hybrid geoid model of, NAPGD 2022, and the geoid model will is going to be named Geoid 2022. Everyone who's interested in the things we're talking about today should probably grab a copy of these 3 documents about the blueprint for the modernized NSRS. Part 1 is the geometric coordinates and terrestrial reference frames. Part 2 is the geopotential coordinates and datum. And part 3 is working in the modernized NSRS. If you did get a copy of these maybe a year or so ago, go back and download them again because they have been updated. Now we're going to review, we're going to get the details of what I was just talking about. Here's a point P that has 2 sets of coordinates and they're equivalent. One set is the Cartesian coordinates for that x, y, and z axis of x, y, z. And the other one is the latitude, longitude, and height, ellipsoid height. And so those 2 are equivalent to each other. And depending on which ellipsoid definition you use, you may get different ellipsoid numbers, but GRS 80 and the parameters that are being used today are likely to change, if so little in the future, as to be irrelevant for most of us who are listening and participating in this program. I mentioned the Euler poles. This slide that was captured from an NGS presentation shows the velocity field of the North American plate. It also, if you look toward the southeast, you'll see something different going on east of Cuba, and you'll see that parts of California seem to be twisting in a different direction. That's all correct. However, if we get coordinates for the Earth-fixed, Earth-centered, Earth-fixed coordinates, they will, they're wonderful. They're the basis for everything we're doing. But if we then use them alone to determine our position, we still haven't accounted, and we'll be showing our coordinates will have a velocity, benchmarks will have a velocity that is represented by this rotation. But in the new system, the Euler pole, which would be the axis of this rotation, is found, and is the velocity, the rotational velocity, is being applied so that the next result of that is to negate these rotations as far as the local coordinates are concerned. Just as a quick refresher for many, here again, orthometric height is when you combine, it can be discovered by combining both the geoid height and the ellipsoid height. This illustration shows things that are fairly typical, but in South Louisiana in particular, the ellipsoid is typically over the terrain, not under, but the equations all still work. Here's that slide once again. And now, though, the long line that goes from the gravimetric geoid is the one you would use to calculate, would give you the big H instead of the hybrid line that you see at an angle up there. And there's a difference applying the gravimetric geoid versus the hybrid geoid, because there's a slope involved, has this sort of difference, a one-time, if you will, adjustment that needs to be made to get to the more truthful gravimetric elevations and using the gravimetric geoid. Much less to the southeast and much greater to the northwest. Step 5 is to create state plane coordinates. They're being scaled to the topography instead of the geoid or the ellipsoid. Those of you who've been around long enough to have to do it, you might have measured some distances on the ground and you needed to make coordinates out of them, so you had to scale them down to NAD 27's sea level, or so that because that was the surface that the state plane coordinates were based upon. And so if you're above sea level, not such a big deal here in Louisiana, but if you were certainly out by the Rocky Mountains or whatnot, very big deal. The scale that goes takes you from what you measured on the ground to what your coordinates would have was significant. NAD 83 did something similar, except that in NAD 83 it was scaled to the ellipsoid. In fact, back to the 27, it was scaled more or less to the ellipsoid because the ellipsoid was meant to be, the ellipsoid model that they used was meant to fit what they estimated sea level to be across the continent. So in both cases, that was a standard method, except for most, for NAD 83 in South Louisiana again, and for a good part of it, the ellipsoid now is above us, and so you'd have to scale up to the ellipsoid. 2022, we should begin to really mitigate any errors that one would make by mistakes in scaling or forgetting to scale or whatnot, because the NGS is graciously calculating new zones for everyone, and one of their criteria is to try to do the scaling of the definition such that it scales well to the mean topography. So in Louisiana, that's pretty good because we're not mountainous. We tend to have, as compared to many other states, we're pretty flat. And the tool that one uses to convert coordinates and do transformations is NCAT, or the NGS Coordinate Conversion and Transformation Tool. All of these things that I've talked about are pretty well explained, and probably a lot more rigorously explained in the 3 documents I cited earlier, and all can be found on NGS website. So what are we coming up with? We're defining a new Louisiana plane coordinate system. The boundaries will be the same as we have traditionally held. The same parishes will be in the same zones. We've got Louisiana North, Louisiana South, Louisiana Offshore, but we are creating a new, especially with the mapping and the GIS people in mind, a new statewide special zone. For example, this is the preliminary estimation of the results for the Louisiana North, you will see that it has a central parallel. Those who are very observant may notice that it has a central parallel instead of two parallels. Because of the method of scaling, there's no difference in having a single or two parallels as far as all the math is concerned. But you'll see that by this legend on the right, that the scale factors are pretty good all the way until you get to the very edges of the zone. So you have a distortion value that doesn't exceed 118 parts per million. So it's pretty good for everything except really precise work. In South Louisiana, it's similar. It's a little flatter, and therefore the largest, let's see, largest, it looks to me like it's 40 parts per million. The statewide zone is an oblique Mercator projection, called oblique because you might see that the central line is skewed at an azimuth of 53 degrees in some. What this does is allow the extents of the projection and its distortion to be minimized best over the area that we've got concerned. In Louisiana, in this case, has mostly a northwest to southeast arrangement, and this is many times more reduction of distortion than the more often used UTM projection. So I think this should probably be something welcomed by those who have statewide projects or the like. New legislation has several purposes. One is it brings the various statutory entries into one place. Some people call that a housekeeping issue. We have gained some time because of delays in the 2022 rollout. The estimate now is that it will probably be 2024, maybe 2025 before everything's officially out. The NGS, when they started this a few years ago, was asked for representatives from 3 groups in the states with 1 point of contact. And our 3 groups, one was to represent the local, the state surveying societies, and Stan Ards, the past president of LSPS, president at the time of the formation of the committee, Eric Lanier, who is the DOTD Location and Survey Section, representing the Department of Transportation, and the third was to get, if there was one, a geodetic research area in the state, and I represent the state in that regard. And if you need more details, find my email address down there at the bottom. The JCAVEL1 at lsu.edu. On behalf of all the people in the photograph here, our team at C4G, thank you for your participation, and anytime we can be of service, that's what we try to do.